Welcome to Transfer Phenomena in Bioprocess Engineering, week 3. So, week 1 and week 2, we started to discuss Reynolds number, dimensions number, how this one. So, then what are the different type of Newtonian fluids, non-Newtonian fluids, all we discussed in the week 1 and week 2. So, today, the week 3, lecture 1, we discuss about introduction to boundary layer, because that is very important, the boundary layer here. So, first we will see what is a potential flow. The potential flow here, it is a mainly the fluids depends strongly whether or not the fluid under the influence of solid boundaries. So, here what is the ideal fluids here? Ideal fluids here, one that is incompressible fluid, of course you know that one, compressible and incompressible. So, then incompressible normally come liquids. The compressible fluids always gases, this all. So, it should be a incompressible fluids, then has a zero viscosity, we always call as an ideal fluid, but normally ideal fluid is not possible, okay, that is called ideal fluid. We always write ideal gas, same way here also. And then the flow of such an ideal fluid is always called a potential flow. So, and it is completely described by the principle of Newtonian mechanics and conservation of mass. So, the potential flow has the two important characteristics here. So, neither circulation nor eddies can form within the stream. So, that the potential flow also called as a irrotational flow, is called as a irrotational flow. Then the friction cannot develop, so that there is a no dissipation in mechanical energy into heat. So, the fundamental, the principle of fluid mechanics is normally studied by Prandtl. I think you know Prandtl numbers, many things are there, the Prandtl 1904. So, here what is the boundary layer? What is the boundary layer? So, the boundary layer here, the fluids moving at a low velocity or high viscosity, because whenever the viscosity is high, the velocity should be low, and velocity is high, always the low viscosity, this one. So, the high viscosity, the effect of solid boundary on the flow confined to a layer, the fluid immediately adjacent to the solid wall. That is, the solid wall is there, okay, the near this one we always call as a boundary layer. So, the outside boundary layer, the potential flow survives. The most technical flow both are best studied in the fluid stream has two parties, one is the boundary layer, other one is the remaining fluids here. The flow through pipes, the boundary layer fill the entire channel and there is no potential flow. If it fill completely entire channel, that is called there is no potential flow here. Next is a streamline. How the streamline here? When your fluid flow through the pipe, this is a streamline, just see here, this is a streamline, flow through the pipe over a solid object or some other, okay, the variance depend on positions. So, here the one way of representing this is, we always call the velocity is a streamline. The variation of velocity is a streamline which follow the flow path. You can see here the flow path is here, the streamline. It is a straight tube, how the streamline behave here. It shows constant velocity, throughout the constant velocity is a constant, that is only this going like this, constant velocity shown by equal distance, this is the equal distance, it is a parallel, it is a parallelly moving, it is not a series moving, it is a parallel streamline, that is shown in the figure 1. So, next is for the velocity profile is here, you just see some objects are here and how the submerged object, how the fluid is flowing from one place to other one. So, the reduced spacing between the streamline indicates that the velocity at the top and the bottom of the object is greater than the front back, because that is here you just see here the difference always here. So, definitely the velocity should be a difference or here. So, normally the slow fluid always the flow we always call as a streamline or laminar flow or streamline or laminar flow. Whenever the motion is very fast, the fast motion, the fluid particle frequently cross on the recross the streamlines. This is always we call as a turbulent flow. The turbulent flow we call as a, whenever the motion the very high, so the definitely the turbulent flow it forms the eddies, because already we discussed the Reynolds number NRE is the less than 2100, we always call as a laminar flow. If it more than 4000 Reynolds number, we always call as a turbulent flow. So, So, the last classes we discussed all this one. So, now we discuss boundary layer. Already we discussed what is the boundary layer. It is always near the region or near the solid where the fluid motion is affected by the solid boundary. There is the boundary layer here. In the bulk of the fluid flow usually governed by the theory of ideal fluids. Then again here the boundary layers define the part of moving fluids here where the fluid motion influenced by the presence of solid boundary. As a specific example of the boundary layer formation, consider the flow of fluid parallel within the thin plate. So, the velocity of the fluid upstream the leading edge, the plate is uniform across the entire fluid stream. So, you assume here, this is here, the velocity of the fluid, assume the velocity here, the surface, the velocity of fluid at the surface at the interface, there is you assume this is a solid phase and this is a fluid phase. This surface, the velocity always 0, the V is a 0, but the shear stress is the maximum. We already also discussed the shear stress is the maximum at this point, but the velocity at the fluid, the interface is a 0. The velocity increases with respect to the distance of the plate. So, example here, definitely here the velocity will get increase. So, each of the curve, this curve, they are discussing this curve, okay, each of the curve, the x distance here, anyway we will discuss this one. This shows the value of the distance from the leading edge of the plates. The curve changes slope rapidly, near the plate, this is near the plate. So, they are saying that the slope of the curve very okay, change very fast there one, rapidly change there one. So, that the local velocity approaches the velocity of the bulk fluid motion. This is a graph for boundary layer here. This velocity u is the velocity here. You can see here the u is the velocity. Then u infinity is the. So the first is this boundary layer, the parallel boundary layer. X is the distance from the leading edge. The x, where is the x here? X is here. X is the leading edge of that one. Then u infinity is the velocity is the undisturbed stream here, u infinity here 1, okay, just for our understanding. So, Zx is the thickness of the boundary layer, Zx is the thickness of boundary layer, here see, Zx is the thickness of first one. So, they say Z dash x were different, okay, the boundary layer thickness here, this is a boundary layer thickness. So, the u is the local velocity, we call as a local velocity, some flows, okay, some velocity should be there. So, then A, B, C, A dash, B dash, C dash. So, there is a A, B, C, A dash, B dash, C dash, all the velocity versus distance from the wall. Then the curve point is here, the C dash, C double dash, this is a curve point. The OL is the outer limit of boundary layer that we call the vertical scale of this one. So, this is very simple for representation of the boundary layer, the parallel boundary layer here. So, the local velocity and how this behaves here and what is the boundary layer thickness of this one. So, everything here. So, the OL, that is outer limit, the velocity changes between the line of and the trace of the wall. So, the OL is the outer limit, the OL is here, outer limit of boundary layer, here. So, the outer limit of boundary layer represents the imaginary surface that separate the fluid stream into two parts, that there is a two part is there. So, one which the fluid velocity is constant, other is the velocity varies from 0 or the wall to the substantially equal to the undisturbed fluid here. So, the imaginary surface separates the fluid that is directly affected by the plate from which the local velocity is constant equal to the initial velocity of approach of fluids. So, this only we discuss here, then the zone or layer, whatever the layer of this plate, okay, the dashed line, here the dashed line, this is a dashed line, this is a dashed line of this one. So, that is called the boundary layer of, okay, the boundary layer, this dashed line, the plate is the boundary layer here. So, the formation and behavior of boundary layer are mainly important, not only the flow of fluids, but also the transfer of how the heat and mass transfer, and then that is only we are studying this one, okay. The heat transfer, mass transfer, not only this flow, okay, the formation of boundary layer, this is very important. So, the boundary layer formation straight tube, what happened here, that is a figure 5 here, this we are going to discuss only this one. So, this point, the boundary layer begins to form the entrance of the tube, the fluid moves through the first part of the channel, the layer of thickness, this one, you can see here, and this is the first spot, is a constant velocity. The first spot, the boundary layer starts from here. Okay. Then during the stage of boundary layer occupies only part of the cross section of the tube, the initially, but after some time the core of fluid flow in rod like manner, it's a constant velocity and annual boundary layer between the wall and core. What the here, see it's started here, then this is a boundary layer, the slowly, okay, the boundary layer, just see here the boundary layer of this one. So this is a boundary layer and slowly goes to center point. So finally boundary layer disappears here. So the boundary layer velocity increases from 0 or the wall and the constant velocity existing in the core. The velocity is the point of core, the velocity is a constant, but it gets increased slowly, the boundary layer this one, because the near wall always, this wall, near the wall here velocity is always 0, but this point is velocity is a V max, the maximum velocity. Wherever velocity maximum, the shear stress is the 0, but if there is no shear stress, then it's a 0, and if wherever velocity is a 0, there is a tau equal to tau max, the maximum we can see here. Okay. So as the stream moves further down the tube, the boundary layer completely occupying the increasing portion of the cross sections. Okay. So you can see here, this is a symbol, this one, the development of boundary layer in the flow in the pipe. So finally the downstream from the entrance, the boundary layer reaches the center of the tube, So after some time, the boundary layer reaches the center of the tube. It's like a rod like core disappears and the boundary layer occupies the entire cross section, that one. So at this point, the velocity distribution, the tube reaches the final form. There is the final form here, as shown in the last curve on the right. Okay. So then there is such a flow with the unchanging velocity distribution is called as a fully developed flow. That's called as a fully developed flow. There is no unchanging velocity here. So it's a very simple here, the development of boundary layer flow through circular pipe. It's a very neatly here. So delta, this is the boundary layer thickness. You can see here the delta. We call the delta is the boundary layer thickness. The delta is the boundary layer thickness. Then R is the radius of pipe. Okay, the R is the here. R is the radius of pipe. So then xt is the transition length. This one. Okay, it starts with 0. This one is the transition length. X equal to xt. Xt we call as a transition length. That one. Then of course v is the velocity. So this is a potential flow regime. You can see here potential flow, how this one. Then of course this is called as a boundary layer flow. How the boundary layer flow. Completely after some time, it completely boundary layer is slowly increase this one. Then completely the boundary layer fully form that one. So this is a development of very simple to understand. We are giving the development of boundary layer flow in the pipe here. So now how to measure the transition length now? The transition length we always call xt. Xt is the transition length. Here already we discussed here. Xt is the transition length here. So there is a two type of flow is there. One is the laminar flow. One is the laminar flow here. Another one is the turbulent flow. So here you just see here the velocity varies. First we discuss this one. So this is called transition length, or we always say entry length. Entry length. Both are same here. Since the velocity varies not only the tube, but with the radial distance of center of tube. So the approximate length of state of the pipe here, the xd by d equal to for laminar flow 0.05 RE. That's the Reynolds number. So of course you know Reynolds number equal to dV rho by mu. So d stands diameter, then v is a velocity, rho is a density, then mu is a viscosity. So there is a two force, this is a ratio between inertia force by viscous force, we call as the Reynolds number. So here the xt is the transition length and the d is the diameter of pipe. What type of pipe we are using here? The d is the diameter of pipe. So in case last we discussed a laminar flow, now is the turbulent flow. In the turbulent flow is completely independent of Reynolds number. So we can see here the turbulent flow independent of Reynolds number, there is no Reynolds number here. So we can write the transition length or entry length, this one xt equal to 50 of d, diameter of that one. So there is no, whenever it goes to Reynolds number for turbulent flow, the transition length is independent of that one. That's only we are giving here. We will see one this one. Yeah, here the same thing at the finite, okay, the distance from the entrance here, after some time the boundary layer merges, that one is a disappear also. The flow is then entirely viscous, then the axial velocity adjusts slightly for until at x equal to this one. So, the downstream of x equal to LE, this one, the velocity profile is constant, the wall shear also constant, and then the pressure drops linearly with the x, either laminar flow or turbulent flow. So, we will take a small problems to understand here. The water at 20 degrees centigrade, the flowing through the tube, the having diameter is 0.02 meter. The diameter is a 0.020 meter. The velocity here given already problem 0.10 meter per second. Calculate the entry length. First they are asking what is the calculate the entry length. Same way for calculate the entry length for turbulent flow. So then the problem already given here, the rho is the density of the fluid here, water, then mu is the viscosity of water. So already d is there, d 0.02 meter, then velocity 0.10 meter per second. So NRE, you know NRE equal to dV rho by mu. So you know d value from here, then velocity of course you know that one, the density also already given here, viscosity, from there we have to calculate the Reynolds number. So the Reynolds number here, after calculating we got Reynolds number 1985. So once you know this number, you just substitute here. Now we know laminar flow, we have to use only for xd by d, this formula. So already we discussed this one, xd by d equal to 0.05 Re, already we got Reynolds number, you calculate from here. So the entry length here only 1.99. So that's the transition length or entry length 1.99 meter for if it is laminar flow. But the same flow if it turbulent, what will happen here? So we always use a xt equal to 50d, that is the formula we discuss here, xt equal to, here see xt equal to 50d here. So xt equal to 50d, you use this one, then you know the diameter of pipe here, you just substitute, then the entry length or transition length xt, we got 1 meter. So for laminar flow, the length is getting increased, for turbulent flow, the transition length of this one getting decrease of that one. That is the final concept here. So next is the boundary layer separation. Here you just see the direction of flow here, the initially the uniform velocity, there is a submerged object is there, object. So here when the flow is started here, you just see what happened the flow for the solid surface. Initially the flat plate, using the flat plate is here, the parallel to the direction of flow. We are keeping the flow and then the plate both are the same direction. The flow is here, the plate is also here. So the boundary layers on the two sides of plate have grown unto a maximum thickness here. For a time after the fluid leaves the plate here, leave the plates, the layer and velocity gradients also it is there. Then soon, however, the gradient always okay, the fade out, the boundary layers mingle and disappear, then fluid once more the uniform velocity. Whenever you move that one, everything will disappear. So the same plate, if we keep in terms of vertical, the last one is we kept as it is the flow direction, but now the same this one, the plate we kept as vertical here. Now what is here, this one? So the turned right angle here, the direction of flow. So now you just see here, once this uniform velocity once hit the flow here, it forms a lot of eddies, that's called a large eddies. You can see here lot of large eddies are here. So the zone we called as a wake zone, this zone where we here that we called as a wake zone. When the fluid reaches the edge of the plate, this edge of the plate then started to move like this. So then this place lot of eddies are forming here, that's why turn around edge. So that's called as a wake zone, we form lot of large eddies here. So the behind the plate, the backwater is this one, the large eddies, that is a large eddies are forming here, that we are discussing here. The zone we called as a wake, the zone is a wake zone. You can see here this zone we called as a, whatever the zone we always called as a wake zone. So, eddies in the wake are kept motion because of the shear stress between the wake and separate the current here. Separate the current. They consume considerably mechanical energy and may lead to a large pressure loss in the fluid at place. So, the boundary layer separation here occurs in the abrupt changes in the either magnitude or the direction of fluid velocity is to create the solid surface. So, here considerably the energy associated with a wake, this energy taken from the bulk flow, the energy is where they are taking from, it is a bulk flow is taking here. The formation of wakes should be minimized if the large pressure loss in the fluid are to be avoided. Okay. So, same way here, then the flow force emerged objects here. So, the forces here, the u infinity, already we discussed the velocity of this one is using the sphere. First we use a plate, then what happened the sphere here. If once this will hit here, then this turbulent eddies form here. Already we discussed a lot of eddies are here. Once hit here, the lot of eddies are here. So, that is called a drag here. The force in the direction of flow exerted by the fluid is solid, this solid called as a drag. So, here the stationary, this smooth surface, the sphere diameter we consider dp, dp is the diameter of particle, the sphere situated in a stream. Velocity is far away from the sphere, that is u infinity, u infinity is a bulk velocity, u infinity we call as a bulk velocity here to the right. So, except the very low velocity, when the flow is entirely laminar, the wake immediately downstream from the sphere is unstable, and when it goes to turbulent vortices will be constantly shed from the various locations round the spheres. So, here there is a two type of this is there, one is a form drag, another one is a wall drag here. So, here this is the pressure on the downstream side, the sphere will never fully recover to that upstream side, and there will be a form drag at the right of the spheres, that one. Same way here the wall drag, because of velocity gradients that exist near the sphere, there also will be a net viscous drag, that is called a wall drag here. So, if you want the sum of the two effects is known as the total drag force, Fd equal to, we have to add for like a form drag, then wall drag, that is called the summation of total drag force is the Fd here. So, the form drag can be minimized by forcing the separation towards the rear of the body. This is accompanied by steam. You can see the figure. So, next is the drag coefficient. So, the drag coefficient here. So, we always call F is the friction factor. This is the friction factor. This is the correlation of geometry, the flow characteristics of solid objects suspended under similar concepts and formed to the friction factor. So, there is a Reynolds number correlation given for the this one Reynolds number correlation here. So, here the F is the friction factor is the tau, we call the shear stress here is a density, then time velocity head v square by 2 is the velocity head here. The product of density then the time, this is called the friction factor F. So, here the friction factor F equal to tau by rho v square by 2 is the product of density, then the velocity head here, and this is the shear stress. So, that is we call as a, we already discussed on time and stress problem also in the last class. So, same thing here. Okay. So, here the velocity head is rho v square by 2, the total drag force per unit area. So, this is called a drag coefficient CD. So, what is CD is defined as the ratio of total drag force per unit area. So, the area of AP is the particle is pi dp square by 4, area of this one in the project area sphere, the direction of and R is the R and M is the property of the fluid here. So, the drag coefficient CD equal to FD by AP, AP is this one AP, area of this one, FD by AP, then the velocity head is there, then the density also here. For cylinder exists this one, we already write AP equal to LdP, L is the cylinder length here. So, similar to F, the CD is a function of Reynolds number, the CD is drag coefficient is a function of Reynolds number only. The drag coefficient is a function of Reynolds number, The Reynolds number we can write dV rho by mu. The dV rho by mu we called as the Reynolds number here. So here the comparison here we draw the Reynolds number NRE number here. It starts with 0.01 and then 100 here, and other side the drag coefficient CD. The CD, you know, CD is the ratio of FD by AP, then rho of this one, the drag coefficient. So it goes to like 0.1 to 10, then okay, 10,000, like these values are based on Reynolds number is there. The sphere already given here. The log plot of drag coefficient as a function of Reynolds number here. So there is a three distincts this there. If it whenever Reynolds number NRE, that we know NRE equal to dV rho by mu, if less than 1, NRE less than 1, we always call as a laminar. So that CD NRE is a straight line. The CD we can use 24 by NRE, normally given by Stokes law. We will discuss the forthcoming classes for full days bed, packed bed. So that part we can discuss Stokes law here. So if the same Reynolds number 1 to the 1 to 1000, but it's a less than this one. So then the CD, the drag coefficient, we have tried for 18 NRE into minus 0.6 here. So if it this Reynolds number is start with 1000 to 2 into 10 power 5, then it's a turbulent region, because whenever Reynolds number cross that one, then the CD is a 0.44 independent of Reynolds number here. That means that whenever the Reynolds number increase, the CD is the drag coefficient is not a function of Reynolds number. That's why they are saying that up to 1 the CD, the drag coefficient is a function of Reynolds number 24 by NRE, but whenever if you get increase, the CD varies here, that you can see NRE here. So it's very important, the flow orientation is, if you want to study, it's very important for drag coefficient with the orientation of solid to the flow direction. Thank you.